Hey, Giovanni, do you have any questions before we start, bud?
No, not actually. I do have a request.
Okay.
Could you change the due date for the face-to-face test by 1 day to next Thursday?
Yeah, in fact, I've essentially already done that. I just changed the practice test so that you have it to take it all the way through 11:59 on Thursday. So, yeah, you can definitely take it up through Thursday of next week.
Yeah, because I have to drive about like an hour and a half, and so I was hoping I could just make it on the same day as the lab, so I can just make one trip.
Gotcha. Yeah, that's no problem.
All right, thank you.
You're welcome. Let's see.
One other thing with you know how with banked curves you split the normal force into components, right?
Uh-huh.
But why is it with like with other inclines you change the weight into components?
With this one, what you're trying to do is you're trying to make sure the acceleration is horizontal because when you're doing a bank curve, you're turning around like this, and the center of the circle is horizontal. So you could actually work it with a tilted coordinate system, but you would have to solve for a two component acceleration where you have an acceleration component that is parallel to the road and then a acceleration component that's perpendicular to the road such that the two add up to give you mv squared over r and that points horizontally inward, which is neither perpendicular nor parallel to the road. So because of that, it's actually a lot easier to work F equals ma in the traditional vertical y direction and the horizontal x direction. And then therefore you can just leave the weight in the mg being a negative y component. Yeah. Whereas the actual acceleration and therefore the normal force will have to be broken down, but the acceleration doesn't have to.
Okay, because I did have a question in one of the practice tests, which I'll ask it once we're finished with everything. Um, it was in chapter 5, just so
Was it
you
one of
don't
the
have
ones
a
asking about the normal force being what is
yeah,
the
it
normal
was
force?
like yes, a 600 kg car is going
That's the one. Yeah.
at
I
some
actually tried to
speed.
address that last night. I haven't figured out exactly what's going on with that. I think I have to solve it uh using the angles of stuff they gave us. And then work out what the normal force is. I haven't been able to get that answer though yet. But like I said, I haven't been able to take the time to solve it really from front to back. I hope to do that. I wanted to do that last night, but I didn't get it done. I'm hoping I'll get it done tonight. But when I can address that, I'll make a video so that everybody understands it, and I'll post it, and then I'll let everybody know.
Yeah, I just guessed and I got lucky with it. So
Yeah,
I'm just
one of those
remembering
kids
that
I spoke
question
to, they got the right
specifically.
answer, but they had Googled it and found it on like Chegg or something like that, but they couldn't figure out how they got it, which was the same issue I was having. So,
Yeah. All right. All right, that's all I had. Thank you.
yep. I had tried mg over cosine theta. I'd also tried mg times cosine theta, which is a normal thing. None of those worked. Yeah. I did find out what the answer was, but it was I can't remember now. It's like 1200 and something or 1500 and something. Is a very much smaller than 600 times 9.8. Okay, so see that. All right, gotcha.
Also one other, this one was just one thing that I thought up of while I was by myself,
Okay.
which it was so like the force of friction on a level plane is like the coefficient um and the normal force, right?
Right.
And so I was thinking, so it's like it's because when I was in a different class, I was just doing it where it's like if you have your finger on the on a desk, right?
Hmm.
And it's not that hard to move, but when you press harder on it, it's harder to move.
Right.
So I was thinking that what changes if the
Ah,
so it's like obviously the mass and gravity and I don't know if like the coefficient changes so that it's harder to move or
no, that's actually a good discovery that you made, and it's something I try to point out, but you might have missed it because it's just words when when someone's telling you. But
yeah.
what happens is you have to solve the sum of the forces in the y direction is equal to zero. Eh. And they're equal to zero because the object's like going to be sliding along a floor. It's not going to be accelerating upward and downward. But what happens if you're like, let's say you're pushing a crate like this, that actually has a downward component and a vertical and a forward component. The forward component goes into the work and fights the friction directly. But the downward component, when you solve for the normal force, that actually makes the normal force larger.
Hmm.
So it's really the friction getting larger specifically because the normal force has gotten larger because you're pushing down on it.
Okay.
But if you, for instance, try to tie a rope to something and then pull it, and you're pulling it in such a way that you're pulling up on it a little bit, that actually decreases the normal force too. So in that way, you can actually use pulling to decrease the friction force, and you can use pushing to increase it. Yeah. Good gosh, I don't know
Okay.
what I got on my back. I sat on something really with a lot of lint on it, evidently. Did you understand that, Giovanni?
Yeah.
Okay.
Thank you.
No, you're welcome. Thank you for chatting me your first and last name, Miguel and Giovanni. Feel free to go ahead and do the same thing, everybody. Uh, It is actually time to start, and again, I'm yawning. I don't know why. All right, got another person coming in. So we need to start pretty soon, but I want to go ahead and give more time. We only have 5 people in the class so far compared to the like 12 or whatever that we have in the class. So ideally we get a few more. Uh, how's it going, Alec? What's the logo on that
It's
sweatshirt?
going good. How are you?
All right.
It's actually a bakery that's out in Lake Tahoe. My buddy
Okay,
worked out there as a culinary student, so
cool. I saw the
yeah.
S. It kind of looked like the Scuba Pro S from
Oh
Scuba
yeah, yeah,
Diving. So I didn't know if
yeah,
it was that.
yeah. Very similar.
Actually, it's been a while since I've seen the Scuba Pro S, so they might have changed it quite a bit. I haven't been diving in the heck 10, 15 years, so I
Yeah.
don't even know if Scuba Pro exists anymore.
Yeah. Who knows? Mm.
All right, well, let's go ahead and get started. I know it's not really all of you here. Go ahead and chat me your first and last name. Uh, And what we're going to do is we're now going into completely chapter 8. Last time I sort of started on chapter 8, which is on conservation of energy. Only I do it a little differently. I include some terms that allow us to take into account non-conservative uh, forces being applied. Your book does that too, but your book just does it as delta U plus delta K and I think they will go plus the work put in is equal to zero, and that's the work put in by non-conservative forces. So that actually does a lot. Eh, but I've not found that very convenient to solving problems of conservation of energy when there's non-conservative forces. So I came up with my own version that I used when I was a student, and it's worked pretty well, and I've used it for years in tutoring as well as teaching. So I'll show you that one as well. Uh, Looks like looks like my iPad's almost completely charged, so I'm just gonna put the charger away and I'm gonna go
Hey,
ahead and share
Professor,
my, yes, sir.
sorry, I just had a quick question for the test.
No problem.
Um, so I have it scheduled for Friday. And I was just looking at Canvas. I know last time the test was already populated under the face-to-face test.
Right.
Um,
That will
what
be where
is
it
this going to
is.
be
I haven't
chapters
made it
5
yet.
and 6?
Yeah, it should be
Oh,
right
okay.
in
Okay,
the
gotcha.
face to face right below that. And it should be
Okay.
posted tonight. I apologize. I actually had one student show up today to try to take it, but they didn't let me know. So I mean I would have made sure I got it ready, but I
Yeah. No, I
couldn't.
got, yeah.
Yeah,
Yeah, I just wanted to
it'll be
let you
there,
know.
but
Yeah.
let me know if
Yeah,
I
no,
can.
it's all good. I just want to make sure it wasn't somewhere else
Yeah,
or
yeah.
something. Okay.
Good job. I appreciate it. Yeah, and
Yeah.
that's always helpful to know because when you go to testing center, they have no idea where it is. So,
Yeah. Yeah. Yeah.
all right. So, what I'm going to do is I'm going to give you a prescriptive way of going about determining yeah, yeah, what a potential energy function is. If you actually look at your book, you should be able to look in chapter 8 and see where I've highlighted specific comments. But one way we can actually do, or one thing we can actually do to compute what the potential energy function is we can actually calculate the change in potential energy by setting it equal to, now this is key, the negative of the work done by the conservative force. So if you actually use that, you do a calculation of the work done by a conservative force in getting from point A to point B, one thing you should immediately notice is that the result does not depend on what path you choose. If that's the case, then you can be pretty confident that you do have a non-conservative force. But also, if you now take that work done by the non-conservative force and moving it, say, from point one to point two, if you multiply that by -1, that will be equal to the change in potential energy in going from potential energy 1 to potential energy 2. So in going from point 1 to point 2. So that's our prescriptive method of solving or determining what the potential energy function is. So I'm going to start off with using that idea, and I'm specifically going to imagine picking up an object near the surface of the Earth. And when I say near, I mean such a distance away from sea level. So sea level is roughly the radius of the Earth from the center of the Earth. We're going to imagine being roughly at sea level, but more specifically, you can have a lot of heights. You can even have heights as high as Mount Everest and depths as low as the Marianas Trench. That will be fine. It's only when you start dealing with distances that are comparable to the radius of the Earth that it becomes a problem. So this is going to work as long as your distance from the center of the Earth is is about equal to the radius of the Earth. If it's literally, let's say, within a factor of 10 of the radius of the Earth, then no, that's gone a little bit too far. So if you go to 10% the radius of the Earth, you probably need to use Newton's law of gravity instead of mg. So let us begin with that. I'm going to start by sharing my screen if I can remember to do that. And it looks like I did. Woo, I'm way ahead of the game now. Woo. Okay, so now I am switching to make sure y'all understand it. So I'm going to give you that big key statement. The change in potential energy delta U equals U final minus U initial. The change in potential energy associated with a particular conservative force is equal to the negative of the work done by that conservative force in force, let's say, when the object goes from the initial position to the final position. So that is a way of computing, and your book gives you a couple different ways, but that's a way of computing what that potential energy function is. Remember, I showed you a mathematical theorem basically saying that if one of these statements are true, then all of them are true. And the statements included that F is a conservative force, that the integral from A to B of F dot dl is equal to some u of b minus u of a and is independent of the path. 2, the integral of f dot dl in a closed loop is equal to 0. 3, there exists a scalar function u such that F, the conservative force, is equal to the negative gradient of u. And then, like I said, some other things like that. There's a way of talking about exact differential equations, stuff like that. But that theorem is very valuable. It just didn't give us exactly what we needed to figure out what that delta U was. We sort of could, because when it said there exists a scalar function U such that F is equal to the negative gradient of U, we could learn how to do the opposite of taking the negative gradient of a magnet, or excuse me, of a scalar force, a scalar function. And it turns out that that is sort of equivalent to this definition. So what I'm going to start with right now is imagine an object within, let's say, 10% of the radius of the Earth. So imagine, whoa, Nelly. Imagine lifting and let's just say a mass to a distance within about 10% of the Earth's radius. But imagine using such a small force that the object never accelerates. The reason why, of course, is if we actually imagine the object having such a force on it that it's able to accelerate, then it's going to acquire some kinetic energy, and that kinetic energy is going to disturb our attempt to calculate the potential energy, because all we really want to change is the potential energy. So we're sort of imagining a pseudo-stationary object, one that's literally moving so slow that you can sort of picture it like I'm going to apply just enough force where the net force on it is 0, and then I'm just going to wait for some random particle or atom or dust ball or lint ball to fly by and strike the object so that it lifts up just ever so slightly, maybe by a single micrometer, and then wait a little while longer for another such event to happen, and wait a while longer for until finally you get a final change in height, let's say from y1 to y2. That's the scenario we're trying to picture. So I'm going to do that and try to calculate that work. So what I'm going to do is I'm going to imagine an object of mass m, and I'm going to imagine putting a force on it, specifically a force upward like that. And the force acting on it is in fact going to be a downward force, and that downward force is mg. And I'm going to go further and say that this is the positive y direction, and this that has no bearing on anything is the positive x direction, and this is the negative y direction. Okay. So what I want to do is I want to use the definition above and say that delta U, which is equal to U, let's call it UB minus UA. And let's imagine that this object is actually sitting here initially at some height. So I'm going to put it in another coordinate system. So there's the Y. And there's the X, and there's the negative Y and the negative X axes. And I'm going to say it's starting at a height of Y0, and I'm going to bring, or let's say a height of Y sub A, and then I'm going to lift it to a height of Y sub B. Okay. So it's equal to the, according to the definition above that I wrote in blue, it's actually supposed to be equal to the negative of the work done by the conservative force. So that's going to be equal to the negative integral of the gravitational force. Now, the gravitational force we know is negative mg y hat, in other words, because it points downward. And of course, the formula for work is equal to the integral of f dot dl. And we've learned that that is a path or line integral. And we've learned that when we're doing a path or line integral, we either use the dl to indicate the direction we're integrating, or we use the limits of integration to indicate the direction we're integrating. But in each case, when we choose one, then the other one has to be in the traditionally positive coordinate direction. So in this case, I'm going to say the DL defines the direction I'm integrating. So I'm going to say DL is in fact positive dy j hat. Okay. So the actual direction we're planning on going is again in the positive y direction. Now, in doing that, I now have to put the limits of integration as the small variable y, since I'm integrating with respect to y, to the large variable y. So that means I'm integrating from ya to yb. Again, because I use that minimal amount of force, barely just negative mg, I'm not actually accelerating it. I'm just sort of bringing the thing to equilibrium so the net force is zero, and then maybe just applying a kabillionth or some really, really small amount of force, just a little bit more to move it up so that it's not actually speeding up. When I do that, you can see that the negative in front and the negative mg and the mg are all constants, and the negatives cancel out, and I can pull the mg out in front. So I'm going to get negative times negative mg is positive mg. And now I can use the linearity of the dot product to basically say I pulled the mg out in front. Now all I have left is the dy, and now I'll let the dot products play just between the individual vectors j hat dot j hat, and that's of course 1 times the cosine of 0 degrees, which is 1. And you're integrating from y sub a to y sub b. The integral of dy is of course just y, and then you evaluate it at yb and ya. So you get mg times yb minus ya, like that. And that's equal to UB minus UA. So now from that, we can tell that UB is equal to MGYB and UA is equal to MGYA. And in fact, more generally, U as a function of Y is just equal to MGY, and that is our potential energy associated with gravity. This is the potential energy associated with gravity near the Earth's surface. Okay, so we found one potential energy function. That's really helpful. I'm going to find another now, and we sort of already done it, but this one could be, for instance, the potential energy associated with a spring. We've actually done that before. I think I had a little bit of problems with the actual uh, integral that I did, and I kept getting a negative 1/2 kx squared. The real result should be 1/2 kx squared. So now we'll do that as well. Calculate the potential energy function associated with Hooke's law, which is, of course, F is equal to negative kx. So what I'm going to do is I'm going to draw a scenario where I'm going to have a mass on a frictionless surface on a spring. So here's my frictionless surface. Something like this. And what I'm going to imagine is a spring that normally sets just like this. And maybe that has a mass M, but it doesn't really matter too much because we're not really cared about the mass M. We're caring more about what's happening to the spring. And what I'm going to say is let's create a coordinate system here. And that coordinate system is going to have an x-axis going that way. Let's say I don't want to put my y-axis there. I'm going to put my y-axis right here. And this means x equals 0 implies at equilibrium. In other words, the spring is applying no force at that point. No force from spring. Okay. Now, what I'm going to do is remember that delta U, which is U B minus UA, is equal to the negative of the work done by the conservative force. So I'm going to imagine, looks like somebody else came in. I'm going to imagine stretching the spring so that the spring is now going to look like this. And this position right here corresponds to, let's say, XB, and let's say X equals 0 corresponds to XA. Okay. Now, the force from the actual conservative force is given by Hooke's law as negative kx. And of course, it will be pointing in the I hat direction. So I'm going to take off that parentheses and write that parenthesis, I should say, and write an I hat there. So there's my F. Now my DL, I'm going to use again the DL to point in the direction that I'm actually integrating. So that's going to be in the positive x hat direct, or the positive I hat direction. So I'm going to say that's dx positive. Well, that's really a lot easier said than done. So, sorry, it's going to be positive dx I hat. And now, since I've chosen the DL to indicate the direction of integration, I'm just going to take the limits of integration from small x coordinate to large x coordinate. And the small x coordinate is XA, which equals 0, to XB. Okay. And I know that didn't, wow, that looks even worse blowing up. So XB is what we're integrating to. So you can see right now that the integral has a negative inside of the integrand, and there's a negative out in front. And in fact, the k is a constant, so I can pull the product of the two negatives, -1 times -1. That's just going to make a positive, and I can pull the k out in front. And actually, I'm going to give myself a little bit more room than I had, so I'm going to put that equal sign a little bit lower. And I'm going to say positive k times the integral. Now I'm going to use the linearity of the dot product to write dx times x. And then I'm pushing all the dot product stuff at the end. And I'm going to have I hat dot I hat like that. Okay. But I hat dot I hat is 1. So now the integral of x dx, of course, is 1/2 x squared. But I got the k out in front. So that's going to be 1/2 k x squared, but I got to evaluate it at xb, or excuse me, xa equals 0 to xb, like that. So that turns out to be 1/2 k times xb squared minus xa squared, like that. And of course, that's u b minus ua. So from that, we can reach the conclusion that ub is equal to 1/2 k xb squared, and ua is equal to 1/2 k xa squared. So we can see that u of x in general, the where x is the distance from equilibrium spot, from the equilibrium position of the spring, is equal to 1/2 k x squared. So now I have another potential energy, and I'll say where x is the distance from the equilibrium. Whoa, that's a bad looking B. The equilibrium of the spring to the position of the end of the spring. Now, I'm saying end of the spring, but to be honest with you, when you put a mass on a spring, it's there, especially if it's hanging, there's a good chance that the end of the spring gets all bent and stuff like that. And it might not be a good indicator of what the X is. So you just want to choose something that's consistent and easy to identify. So often, if you have a vertical hanging spring, you would take the distance, let's say, from the bottom of the mass when it's hanging, but it's not moving. You would take that as the equilibrium position, and then you pull it down some distance. Now you measure from the bottom of where the mass was to the bottom of where the mass is. That's a very normal way of doing it. But the main thing is just trying to ascertain exactly how much the spring has been stretched or compressed, and that's what you put in for X. So any questions on that one? Okay, so that's another potential energy. And again, what we're going to do is we're going to have a nice little conservation of energy where you can basically say that the change in potential energy, delta U, plus the change in kinetic energy, delta K, is equal to 0. Now, that's what we mean by conservation of mechanical energy. Now, there's a lot of different ways that you can have potential energy so that U delta U equal plus delta K equals 0. That doesn't mean there's just a single U function. There might be several U functions. You might have a U associated with compressing a spring. You might have a U associated with the height above the Earth's surface when it's close to the surface of the Earth, not like a whole half of the Earth's radius away or something like that. And you might even have other things like the potential due to being in close proximity to another atom or all sorts of crazy stuff like that. So the main thing is you got to take into account all the conservative forces, and therefore you might have multiple U's. And later, once you learn about rotational motion, you'll find out that there's actually multiple types of K's as well. There's a kinetic energy associated with the way the center of mass of the object moves. But then if the object's more than a point particle, it could be rotating like this as well. And there's a whole different kinetic energy associated with rotation that instead of being 1/2 mv squared turns out to be some quantity 1/2 I omega squared. So all of that's going to come to play. But right now, I'm just trying to ascertain what our potential energy functions that we're going to use regularly are. We've done gravity when we're near the surface of the Earth, and I sort of restricted ourselves to within plus or minus, let's say, 10% of the radius of the Earth from sea level. If you got higher than that, then you're definitely going to have to start looking for using Newton's law of gravity instead of mg for the force. So now what I'm going to do is use Newton's law of gravity and compute a potential energy associated with that. Okay. Now, because that law happens to look just like the law for the electric force, we're going to figure out that the electric force is a conservative force as well. And it also looks like the magnetic force. And in some sense, you could say it's the magnetic force could be conservative, but there's actually times where it is conservative, where generally it's not conservative. Okay. So let's go ahead and figure out our new potential energy function associated with the Newton's law of gravity. So what I'm going to do this time is I am going to imagine the Earth as being at the center of a coordinate system. So let's draw a little coordinate system, a three-dimensional coordinate system, like this. And now I'm going to associate this with the x-axis, this with the y-axis, this with the z-axis, and now I'm going to put the Earth right at the center of the Earth, being at the center of the origin. And I got the computer to cheat and make that a pretty circle. Okay. So what I'm going to do is imagine an object, let's say an object here at this particular point, and then maybe later at this particular point, so that you can see maybe it follows some crazy, crazy path, and that crazy, crazy path might be something like that. That's certainly fine. What I'm going to say, though, is our job is to calculate the scalar potential. Okay, that's what we're trying to do here. And what I'm going to tell you is the force of gravity, speaking as an actual vector, is going to be G, the gravitational constant, times big M, the mass of the planet, times little m, the mass of the object, divided by r squared. And notice it's always pointing radially inward. So what do I mean by that? What I mean by that is, let's imagine it being at this point right here. Okay. Radial means essentially from the origin to the point. So a radial line is that black line I have drawn. If I was at a different point, let's say over here, let's say we were at this point, then the radial line would be like that. But what we're going to do is we're going to use the fact that the gravitational force is always attractive, so it's always pulling things towards the center of the Earth. Therefore, we're going to define a little vector r hat such that negative r hat is that little guy. Okay, so when we go to say the force of gravity, we're going to put a negative there and we're going to put an r hat right there. That r hat turns out to be the r hat from spherical coordinates. I'll probably tonight, I'll probably draw a spherical coordinate for you just so you'll have it so you can see it. We're not required to know, you guys are not required to know cylindrical coordinates, polar coordinates, or spherical coordinates, or hyperbolic coordinates, or elliptical coordinates, any of that kind of stuff. I want you to know that they exist, but you're not supposed to know them necessarily. Now, I think everybody probably should know something about polar coordinates at this point, but even then you might not have to. So I'm going to show it to you just so you can recognize the vectors that I'm talking about, because we're going to use them over and over and over again. So this is the gravitational force, and that's what we assume is a conservative force. It is, by the way, I know it for a fact. So now I'm going to calculate this going from a particular distance r. Let's say this distance right here is r sub b. And let's say this distance is RA. And I'm going to actually imagine moving the object from RA to RB. Okay. So now I can say delta U is equal to UB minus UA is equal to the negative integral of basically the work done by the conservative force. That conservative force is gravity, and that's negative G big M little m over r squared r hat, and then that's got to be dotted with DL. Again, I'm going to use the DL to indicate the direction I'm going. A student asked us today, so this is something that might be helpful for you to know. They asked, can I just always use the same plan? In other words, what I interpreted what he was saying, can I always indicate the direction I'm going with the DL and then use the range of integration as just the positive coordinate direction? I said, absolutely. So you can do that. I'm trying to teach you how to do it in general, but if you need to for right now, you just find a way and lock on it. So let's always put the DL in the direction we're going. That would be fine. The direction I'm integrating is obviously from RA to RB. So that's in the negative R hat direction. So I'm going to call that negative dr R hat. And that is going to be the integral, the work that I'm going to calculate. And now that I've chosen DL to indicate my direction, I'm just going to take small coordinate, which is RB, and integrate it to the large coordinate RA, because the default is supposed to be from small coordinate to large coordinate. So any ones that you're not using to indicate the direction you're going, they should just be from small coordinate to large coordinate. And the one that you do choose, and you can only choose one. If you choose both, you're going to screw yourself up. So now we're ready to do this. Notice I have a negative times a negative in the integral, and then I have a negative out in front. The two negatives in the integral, we can imagine them canceling each other out and just leave an integral at the end. So now I'm going to say, darn it. Now I'm going to start it right here and say delta U, which again is UB minus UA, is equal to, I'm going to pull out all the constants, including that negative that we talked about. That's going to be G, M, M. And now I'm going to use the linearity of the dot product, and I'm going to say RB to RA. The linearity of the dot product allows me to say R to the negative 2 dr, and then r hat dot r hat, which of course is 1. Now the integral of r to the negative 2 is negative r to the negative 1. So we're going to now say that negative out in front just became positive. So now I've got positive G M M like this, and then I have 1 over R, and that has to be evaluated at RA first and then RB. So I can now say this is equal to GMM times 1 over RA minus 1 over RB, like that. And what you see right now is that RA, which is really a larger quantity, it means 1 over RA is a smaller quantity than 1 over RB. So what I have right now is an actual negative quantity. Okay, but that's just something to keep in mind. Now, what I'm going to do is I'm going to let UA be the potential where I think the actual potential energy would be 0. Now, the place where the potential energy 0 is when the force is either 0 or so close to 0 that you can't measure it. So what position RA, how far away should we make that to make the potential energy equal 0? Anybody have an idea? Anyone? All right, so what we're going to do with this one is we're going to allow the RA to be infinitely far away. And when you integrate to infinity, hopefully I've learned this by now, you take the limit as the variable approaches infinity. So now I'm going to go ahead and say this is, this is going to be equal to G M M times the limit as RA approaches infinity of 1 over RA minus 1 over RB, where RB is just going to be obviously the distance to point B. Now, in the limit as RA approaches infinity, that first term goes to 0. So we ultimately get negative G M M over just plain RB. So UB is equal to negative GMM over RB. And more generally, that means U of R is equal to negative GMM over R. And that's our new potential energy function. Okay. So that's our potential energy function. If we're dealing with distances that are really comparable to the radius of the Earth, we have to use this. Okay. I will tell you that it gives us some sort of neat results. I'll show you a couple of them, but let me go ahead and introduce what we're going to do as our conservation of energy. So as I mentioned to you, the way your book generally does it, but it actually shows a lot of different ways. So he does pretty good on that. We're going to use the fact that let's say for, I'll say U sub lowercase g. So that's when G doesn't change very much. In other words, when R is close to the radius of the Earth, that U sub G of y is equal to mgy. That's one of the things we use. We also have u for the spring of x is equal to 1/2 kx squared. And we also have u for big G as a function of r is negative g mass over r, like that. The big M refers to the planet and the little m refers to the object that's moving. Okay, so we have those. But when I say conservation of energy, I really mean conservation of mechanical energy. And mechanical energy means energy is not associated with, for instance, bonding, and well, even bonding can sometimes be it, but we'll just say energy not associated with increasing the internal or thermal energy of an object, stuff like that, because there is energy associated with temperature and stuff like that. So conservation of mechanical energy is often written as delta U plus delta K is equal to 0. I've given you the different types of delta U, and that's just a couple of them. There's more, of course, but the K is supposed to be 1/2 mv squared. We'll later learn that that's not correct from a relativity standpoint. There's a different formula for it, but we'll also learn that there's other forms, like there's K is equal to 1/2 I omega squared. That's when something's rotating about its center of mass, say. Okay, so this is a version of conservation of energy, so I'll box it off so you'll know that that's something you can use. But you can also take that and say, remember, the delta always means final minus initial. If we put a delta like you see there on something, you can assume that's what it is unless I explicitly tell you otherwise. And we will later when I do thermodynamics. But right now, what that means is U final minus U initial plus K final minus K initial is equal to 0. So you could rejigger those terms, and then you discover that U initial plus K initial could be on one side, and then you'd have U final plus K final on the other side. And that's yet another way of doing conservation of energy. Okay. But the downside of these are, let's say downsides, cannot deal with non-conservative forces. What I also call dissipative forces. Because imagine this, if you really want to, things like a spring, for instance, if I push the spring in, whatever energy that took for me to push the spring in is exactly how much energy I'll get out if I allow the spring to push back on me. It'll push it to the same distance. If you include friction in that, what you'd see is friction is going to take some of my energy away so that I can't compress it to as large of an X. But then when I start to push it back out, it's also going to not allow me to push it all the way back to X equals 0, because I'm going to lose some energy from there too. So you can see how I'm calling it a dissipative force. So what I've done to account for all this is I've made up my own version of conservation of energy, and that's what I'm going to teach, and what I suggest you use. So this is my version. My version is this. I say U initial plus K initial plus the work you put in. Okay. It's very important that I'm saying work that you put into the system, and it's on the left-hand side. Another thing that's very important with this version is all terms are positive except possibly that U sub capital G. That's one that's always going to be negative because it's defined as negative. So I'll write right here, each term must be positive except negative G M over R. Okay. Any other terms you have to be positive, but that one could be negative, and it'd be negative on both sides. That's the key thing to know. Now that's the left-hand side. The right-hand side is going to be U final plus K final plus, guess what? Work out. Okay. Again, that's got to be a positive term, but notice the fact that it's on the right-hand side means it's equivalent to taking energy away from the initial setup, because if you put it on the left-hand side, it would be negative, because the way you get rid of it is you say minus W out, and whatever you do to one side, you got to do to the other. So then you get UI plus KI plus work in minus work out. That's exactly what work out is supposed to do. It's supposed to steal some of the initial energy you have. So now, in addition to that, I like to add a term for dissipative force. So I also say plus E loss, again, a positive term. Now, in this case, I'm seeing E loss, and I normally reserve that for instance, work done against friction. But if you remember, like when you do a work against friction, the force of friction is like pointing, let's say, to the left, while the object's actually moving to the right. So when you do the calculation, even if the forces are parallel, well, anti-parallel in this case, and even if they're constant, it's force times the distance times the cosine of 180, which gives you a negative. And here I'm saying, no, throw that negative away. We just need that full amount, because putting it over here is, again, just like stealing from the initial energy. So this is the version of conservation of energy I use. And what I tell you about it is, like I said, first, all the terms should be positive. And then second, what you think is WN, I might think is E loss or work out or something weird like that. But also what I think is E loss, you might think is work out. And what I think is work out, you might think is E loss. That's all okay. The main thing you got to remember to do is think of every type of energy and every type of energy dissipation that's going on and account for it, but only account for it exactly one time. Okay. So long as you keep that in your head, then everything will work out. It doesn't matter what you call UI, what you call WN, what you call W out, what you call E loss. The main thing is each of those WN, W out, and E loss need to be positive, and they're basically coming from the absolute value of a work calculation. Okay. Notice I said absolute value because it needs to be positive. So as an example, I will give you the mother of all examples, which is a sort of cruel one. So mother of all conservation of energy examples. So that's what I'm calling this. Now, what I'm going to imagine is there's a little section on top of a hill that's essentially frictionless, and level, and then it slopes down again, essentially frictionless, like that. And in fact, it covers a very specific height. I'm going to say, let's let H equal 150.0 meters. Okay. Now, what I'm going to imagine is there's a little car, a little sled right here, and then sitting on it is a child. Okay. And their mass, including the sled, would be equal to 75.0 kilograms. So it's maybe a slightly chubby kid. The main thing is it includes the weight of the actual sled as well. And what I'm going to say is this kid has a father that is pushing them with a force that is horizontal and has a magnitude of 100 newtons, and they're going to push it a distance of 3.00. That's really small. Let me make that bigger. The dad is going to push horizontally, so we don't have to worry about doing the dot product, because it's obvious that if it's horizontal and the displacement's horizontal, the vector between, or the angle between the force and the displacement is 0. And what I'm going to do is I'm going to say the displacement is 3.00 meters, and that's going to be perfectly horizontal. Okay. So that's dad there. And this is the force done by dad. Okay. Now, in addition to that, notice I can zoom in. So if we need to see anything, you can look at it that way, and you just zoom in like that. But in addition to that, we're assuming all this stuff is nice and frictionless, and the father is going to push her for a force with a force of 100 newtons over a distance of 3 meters, and that's going to be what I would call work in. Okay. That just seems obvious to me. You could, in fact, add another term on the left and say En. So maybe you wouldn't want to use work, or maybe you have two sources of energy going in. One is the work put in by the father, and the other one's like I don't know, maybe a wheel that spins and pushes the kid's head forward and gives them a little boost of energy too. So you could add another term, or you could say there's two work ins. Having a term that's called work in could actually be a stand-in for 14 terms of work in. But we've got what's going on now. Now, what's going to happen is at the bottom of the hill, we're going to immediately run into a friction full surface like this. And what I'm going to say is right there, the distance is, let's say that's going to be 100.0 meters is the distance. Okay. And let's say the friction force is equal to, let's say 9.00 newtons. Now it's a friction force, so it should be horizontal. And if she's going to the right, it'd be horizontal to the left. Obviously, this could be treated as a work out, where you'd calculate the work done by the friction force and then, of course, change the sign to positive. Or you could treat it as a E loss. I'm going to treat it as a E loss. Okay. So that's that. But then at the end of that 100 meters, there is a smooth, frictionless surface on which the child is able to slide. But get this, there is a spring-loaded wall that the child will run into. And that spring-loaded wall has the ability to compress a certain period, but it really is just attached to, like, say, a building or a tree or a car or something like that. Okay. And we're going to say the spring constant for this K is equal to 10,000 newtons per meter. And I'm going to say that has 4 sig figs, and only the last 0 is not a sig fig. So here's the example. In part A, I want to know how fast at the end of the push. In other words, at the end of the father pushing, so I'm going to call this V final A equals question mark. So right up here somewhere, right after the father finishes pushing, but before she's been able to change elevations, I would like to know how fast the child is going as a result of that dad pushing. And then part B, I would like to know how fast at frictionful surface, and I'll call that VFF, or no, let's call that VFB. Okay, C, how far does she get in the frictionful area? Or how fast, in other words, if she makes it the whole way, how fast at end? That would be, of course, VFC equals question mark. And then finally, assuming she makes it this far, D, how far, whoa, is the wall moved? In other words, the girl is going to hit that spring-loaded wall, and that's going to compress the spring, and it's going to keep compressing the spring until her velocity comes to zero. I want to know how far did that spring compress. Okay. Now, I will warn you, there's a good probability that this poor child is going to get some bad treatment. I've made up these numbers really big so that I could hopefully make it all the way to hitting the wall and compressing everything. Okay. So it's not going to be a positive outcome for the poor child, but either way, it is a good conservation of energy problem because it allows you to see all the individual terms. So if I want to, I can now go ahead and take all this and put it on the next page and start working the problem. I think I will do that because it might be kind of distracting to have to go back and forth and refer to it. So what I'm going to do is just copy all this. And now I'm going to come over here and paste it. Sometimes I think I might be a vampire because not always does my touch do anything. Okay. All right. So let's work on part A. Solution. What I'm using for my solution is UI plus KI plus work in is equal to UF plus KF plus work out plus E loss. Okay. And just to make sure we're all on the same page about this, I'm going to make sure that y'all can figure out exactly where the solution starts. Whoa, Nelly. And where the problem ends. So I'm just doing that. All right. So that's what we're going to use. Let's start with part A. So with part A, notice the height of the kid at the beginning and the end are the same. So what I'm going to say is UI is equal to UF, and I'm just going to assign that equal to 0. Okay, because it really doesn't matter. It's something, but the main thing is it's going to be the same on each side, so you can subtract it from each side, and that'd be fine. And you're also allowed to set the 0 of potential energy, anything you want. And the fact that she didn't change heights could mean for this part of the problem, it's certainly fine to call them both 0. Additionally, the initial kinetic energy is 0. The work in is the work done by the father. So I'm going to say work in is going to be 100.0 newtons times 3.00 meters times, in this case, the forces are actually parallel. So this is just 300.0 joules. So that's the work in. The K final is going to be 1/2 mv final a squared. And of course, work out and E loss will be 0. So that's why way I'm going to set this equation up. So that gives me 300.0 joules. That's 0 for the work in, or excuse me, for the potential energy, plus 0 for the kinetic energy, and then 300 joules for the work in. And that's equal to 0 for the final potential energy, and plus 1/2 of 75.0 kilograms times V final A squared plus 0 plus 0. So we can find that VFA is equal to the square root of 600 joules, that's 2 times 300, divided by 75.0 kilograms. Now, a joule, remember, is a kilogram meter squared per second squared. So if I divide by a kilogram, I'm just left with meters squared per second squared. And then when I take the square root of that, I get meters per second, which is exactly what we expect. So in this case, I'm going to take 600 and I'm going to divide it by 75. And that gives me 8. And now I'm going to take the square root of 8, which is 2.828 meters per second. So that's really how fast she's going. Just at the end, of course, that's only good to 3 sig figs. So I'll underline that last one. And I'm going to say this whole thing is my answer. Okay. Now that's not very fast. In fact, I'll give you an idea. 2.828 meters per second is a very small number of miles per hour. It's about 6 miles per hour. Okay. So that was part A. Now, here's the neat part about this. We can choose to say our initial position starts anywhere we want. We could start it at the very beginning, which is before the father even passed, in which case the initial kinetic energy is 0. Or we can choose to start it right after the father lets go, in which case the initial kinetic energy is well, you can see it's basically going to be 300 joules, right? So we can start there as well. It doesn't matter. I'm going to start the second one from the very beginning. And then later ones, I'll probably start it from the most recent answer I've worked out. So let's do part B. Oops. So part B, we're wanting to find out how fast she'll be going when she reaches the frictionful surface. So right at that black dot just before the blue gets scribbly looking, that's what we're working out here. So U initial is going to be M times G times H, and U final is going to equal 0. Kinetic energy initial is going to equal 0 because, again, I'm starting with the father just pushing. I'm going to say work in is actually equal to 300.0 joules. And at the bottom, I'm going to say UF is equal to 0. I already got that. But K final is equal to 1/2 mv final B squared. And also, I'm going to say that work out is equal to 0. And I'm going to say that E loss is equal to 0 because I don't see anything that I need to address with workout or with E loss yet. All the transfer of energy is just changing form from potential energy of being up high to kinetic energy down low. So now I can plug all this in. I'm going to say 75.0 kilograms times 9.80 meters per second every second times 150.0 meters. That's my MGH. My kinetic energy, my kinetic energy is 0. My work in is 300.0 joules. And then my final potential energy is 0. My final kinetic energy is 1/2 75.0 kilograms times V final B squared plus 0 plus 0. So now I can find out that 75 times 9.8 times 150 gives me a big number. That's 110,250. So that's 110,250 joules. Now that's really only good to 3 sig figs. So this 250 is not significant, but I'm going to keep it or else we just can't take into account all the little forces plus or all the little energies plus 300.0 joules. And that's equal to 37.5 kilograms times V final B squared. So that gives me V final B is going to be equal to, I'm taking that 110,250 and I'm adding 300 to it. That gives me 110,550, so 110,550. So that's what that is. Now I'm going to divide that by 37.5, which is half of 75. And that gives me 2948. So now all I got to do is take the square root of 2948. And that's meters squared per second squared. And when I take the square root of that, I get 54.29, which is really, really, really fast. That's equal to 54.295 meters per second. And that's really only good to 3 sig figs. So the 9 and the 5 are not good. But that's our velocity going into the frictionful area. To give you some idea how fast that is, that's 54.295 meters per second. If I add that to 0 miles per hour, that turns out to be 121 miles per hour. So as advertised, this is not a nice, friendly little scenario. So that's, like I said, about 120 miles per hour. It's pretty darn fast. All right. Now we can start part C. Does anybody have any questions on what we've done so far? Okay. So what we can see is really the energy we have going into the frictionful area is 110,550 joules. I can calculate how much work it takes to completely cross that 100 meters. And in fact, what I can do here is I can start my conservation of energy at the black dot just to the left of the frictionful area. That'll be fine. If I do that, then U initial is equal to U final. They're both the same height. So I'm going to call that height 0 and just call the two potential energies 0. I am going to also say that the kinetic energy initial is all the energy that it has. And in fact, I'm going to say that that kinetic energy is 110,550 joules. And that's going to be equal to K initial. And then work in is going to be 0. And then I go to U final, I already did that. K final, in all honesty, K final should be, might be 0, but what I want to figure out is E loss. So let me write down E loss, and that's going to be, of course, equal to 9 newtons times 100 meters, which is, of course, 900 joules. And that last 0 isn't there. Notice that 900 joules is well under the 110,000 joules we have going in. So we know for a fact that it's going to make it completely across. So that part C where I said, how far does she go, or does she get in the frictional area? If this number had exceeded 110,000, then I would have said the E loss would be 9 newtons times X. And then the X would come up short of 100 meters and the K final would be 0. But since it wasn't enough, then K final is going to be 1/2 of 75.0 kilograms times V final C squared. And that's the last term. The work out is going to be 0. So now I can put all this in again, and I'm going to get 110,550 joules. Each of those are non-sig figs. That's equal to the initial kinetic energy. So I'm saying 0 plus that plus work in is 0. All that's equal to final potential energy, which is 0. And then we have the kinetic energy, which would be 1/2 75.0 kilograms V final C squared. And then that is, of course, the kinetic energy final. The work out is equal to 0, as we already showed you. So that's going to be 0. And then the E loss is going to be 900.0 joules. So I can take and subtract that 110,550. I can subtract from that 900. And that's going to give me 109,650 joules is equal to 37.5 kilograms times V final C squared. So V final C is going to be the square root of 109,650 divided by 37.5 gives me 2924. So not a whole lot slower, because before it was the square root of 2948. So now I'm going to take the square root of that number, and that turns out to be 2 times the square root of 731, which is 54.074 meters per second. So that is the final velocity just before she hits the spring-loaded wall. Okay. Now 54.074 is still about 120 miles per hour. So this is not a pleasant thing. A 10,000 Newton per meter spring is pretty strong too. So it's not going to be a nice, smooth little deceleration. But either way, we can go ahead and calculate it. This would be smart to use, since I did draw the blue under the compressive wall, under the wall with the spring. That blue is nice and smooth, so I'm pretending like that's frictionless. So I'm going to start off again with the potential, or with the kinetic energy, or excuse me, with the conservation of energy starting just before she hit the wall. So for D, I'm going to get UI equals UF is equal to 0. I'm going to get that the work in is 0. I'm going to get that the kinetic energy is in fact 109,650 joules, but the 650 are not significant. The work in is 0. The U final we already said was 0. The work out is 1/2. Let's write it this way. The work out is 1/2 times 10,000 newtons per meter times x squared, and the x is what we're solving for. And the E loss, we've already accounted for that friction loss earlier when we subtracted the 900. So the E loss is going to be 0 here. So really all I have is 109,650 joules is equal to 1/2 of 10,000 newtons per meter times x squared. And that's going to give me x is equal to some god awfully big, like 6 or 7 meters probably. So if I take the 109,650 and divide it by 5,000, remember half of 10,000 is 5,000. So I'm going to divide it by 5,000. And that gives me 21.93. So x is going to be the square root of 21.93. And in this case, we're actually dividing joules by newtons per meter. So joule is a newton meter, so that just gives me meters squared. And then you take the square root of meters squared, and that gives you just plain meters. So I'm going to take the square root of this number, and that gives me 4.683 meters. So we can conclude that the frictionful surface was not enough to bring her to a stop. So she continued past the frictionful surface and went into the safety barrier that was a spring-loaded wall, and she ended up compressing that wall 4.683 meters. Now, if you so desire, you can do for extra credit, since our time's about up, you can work this all over again, but start from the beginning every time. And in other words, go to the very beginning using UI is equal to MGH, work in is equal to 300 joules, K initial is equal to 0, and then show me that you still get the same answers. That's a nice little extra credit, and it also gives you some practice using this version of the conservation of energy. Our time is actually up. The only thing that I was going to show you beyond this is we could actually use UI plus KI plus work in plus, or excuse me, equals UF plus KF plus work out plus E loss. We could use this to find out what the escape velocity of a projectile would be to leave the Earth. And all I'd do is I'd put in negative G M of the Earth, M of this projectile, over R, the radius of the Earth. That's the potential energy. Notice I'm actually getting a negative here. And the initial kinetic energy is going to be 1/2 V escape squared plus 0 is equal to 0 plus 0 plus 0 plus 0. And that would give us V escape is equal to, notice the M's cancel out. Oh, excuse me, not that M, but this M cancels out. So that gives me the square root of 2G times the mass of the planet over the radius of the planet, like that. And that turns out to be 11.2 kilometers per second is the escape velocity for the Earth. Not only that, if you wanted the thing to be a black hole, you can do the same thing. You'd get negative GM M over R Earth plus 1/2 MC squared plus 0 equals 0 plus 0 plus 0 plus 0. When you do that, you find out that if you wanted the radius of the Earth to be so small that it acts like a black hole, then you could just solve for r, and what you get, it turns out to be a relativistically correct formula. You would get 2g mass of the Earth over c squared, like that. And that is actually the correct relativistic formula. Now we're done. You guys are free to go. Please chat me your first and last name if you haven't already done so. And be prepared for your tests next week or possibly this weekend. I will have it posted tonight. I'm sorry. I think Mr. Skidmore went today and I screwed up. So I apologize for anybody else that planned on taking it today. I just didn't know, or I would have had it ready for you. I'm going to do that now. So have a good evening. I'll wait for the last person to leave in case anybody has any questions.
I have a question.
You have a question, Jen?
Yes, I do.
Okay.
Where did I write it? I wrote it down at the beginning of class. Anyway, is there an online test for this test?
I haven't made that one either, but yeah, that will be up on probably tonight as well. And
Okay, so
I'm
that is
probably not
coming.
going to make a separate practice test because it's going to be on the same material.
That was my other question, was can you reopen the practice test?
I did that just before class started. I set it
Okay.
to close on Thursday. So I'm actually going to give y'all until Thursday. I might even give you till Sunday of the following week, not this coming Sunday, but Sunday after, just in case we have any problems. I do know that I have, I think, 3 people that still haven't taken test 1. That's a real problem. I'm getting ready to just put a 0 in there, and that's gonna that could be a very good indicator that there's no way to pass once you get a 0. So I'm obviously not talking to y'all. Y'all didn't do this, but hopefully someone else in the video will say, "Oh wow, yeah, I forgot to take my test." I don't know why they haven't contacted me, but anyways, do you have another question, Jim?
So when is the face-to-face test? When do I have to take the second one by?
Definitely by Thursday of next week, but I might even give you even more time. But right now I'm leaning towards just by Thursday of
Thursday
next week.
next week. So we'll have an online test, a face-to-face test. You already reopened
The
the practice test, and this is all for 5 and 6, correct?
Exactly. I'm not adding any more chapters or anything like that.
And then so 7, 8, and 9 will be coming in the
Yep.
future.
Yep. That'll
Okay.
probably be the
Got it
next
all straightened out.
online test as well as the next face-to-face test.
All righty, sounds good. Happy
All right.
Halloween.
Happy Halloween.
you.
Have a good one, Jennifer.
Yep.
What's up, Dylan? How can I help you, sir?
I just have one question. I had sent you a question. I had one of the on the practice test. It was basically one of the questions that said like the thickness of a penny, how many would it take to fill up a room?
Right.
How would you do that without like on a lockdown test and you don't have access to where you can't just Google what the thickness of a penny is?
Exactly. Did it say a room, or I think it gave you a 1 foot by 1 foot by 1
No,
foot
this
box?
one was like a 8-foot to the top of an 8-foot ceiling.
Okay, gotcha. So if they said a particular room, they've got to give you some kind of rough estimate because rooms can vary. I mean, if you look, for instance, at the dining hall of a mansion, that room might have, 1,200 square feet just in that room.
Yeah, well, it said to the how many would it take stacked on top of each other to reach the top of it or to reach an 8-foot ceiling?
Oh, okay. That one's a lot easier. Okay, cool. So since they gave you the 8-foot tall ceiling, you can just convert 8 feet to, some units that you think the thickness of a penny in. What would you guess is the thickness of a penny in, let's say, centimeters or millimeters or micrometers or anything like that?
Well, I looked it up afterwards, but I wasn't sure. But it's a little over, it's closer to like a 16th, I think. I think it's like 0.05.
Yeah. So part of what we're doing in this physics class is you're supposed to be learning a little bit of the SI system. So I tell my students, for instance, that the height of a doorknob is right about 1 meter. If you go to the top of the knob, that's about a meter. The width of your index fingernail, or maybe your pinky, if you're particularly large, is usually about a centimeter. And then the thickness of a good staple is normally about a millimeter, or the thickness of a funky fungified toenail is about a millimeter as well. So I usually picture the thickness of a penny as a single millimeter. But even if you don't know that, what you can do is use powers of 10. So you know roughly how big a millimeter is roughly maybe as thick as a staple is wide. In other words, the little staple that goes like this and this and then this. That width right there is about a millimeter on some of the bigger, more heavy duty staples. But if you think about it that way, you can just say, okay, is the width of a staple or is the width of a penny, the thickness of a penny, is that 1 millimeter or 10 millimeters or a tenth of a millimeter? And you could probably rule out that it's definitely not a tenth of a millimeter. And you could rule out that it's not 10 millimeters because the 10 millimeters would be a centimeter, right?
Yeah.
So that's a way of just going ahead and calling it 1 millimeter. Or if you're really not that sure, you can do what's called the geometric mean. So you could take the one that's 1/10 of a millimeter and multiply it by the one that's 1 millimeter, and then take the square root of that, and that's called the geometric mean. And then you just use that distance. But that you can do that for every unknown quantity. You take the most extreme version of how small or big it is, and then another extreme on the opposite end. For instance, if the first one was how extremely big it might be, the other one could be how extremely small it might be. Take the geometric mean by multiplying them and taking the square root, and you just use that for it. And we always use just pretty much 1 sig fig. Now,
Okay, yeah.
all you have to do is once you've decided it's 1 millimeter, you need to convert 8 feet to millimeters. So 8 feet, you multiply by 12, that gives you inches. You then multiply by 2.54, that gives you centimeters. And then you divide by 10, or excuse me, you multiply by 10, and that gives you millimeters. So if you
Okay.
take that number of millimeters, you could picture yourself saying, okay, here's me taking a stack of pennies that's as tall as the ceiling, and I'm going to take 1 away, 2 away, and you just keep counting them like that. As you're counting them and subtracting them out, that should make you think of the division operation. So you're just going to divide that number by 1 millimeter.
Okay.
Does that make sense?
Yep.
Whenever you see repeated subtraction, think division. Whenever
Yeah.
you see repeated addition, think multiplication.
Yeah,
That's
I knew how to get there. I just didn't know, like, if it were on a test, I wouldn't know the starting thickness of a penny. So once I knew that, I was able to find the answer. But
yeah. They expect you to take a guess from like they wouldn't ask you what's the thickness of a Peruvian coin, because that's not a big currency that
I
everybody
guess it's
knows, and
because
we're
it's
not in Peru.
I guess it's because it's the magnitude question. As long as you're not like 100 or 1,000 off, you'll still be close.
Yeah. Yeah. And they really won't basically within a factor of 10. So yeah, you'd be good.
Yeah. Okay.
All right. Does that help, Dylan?
Yep.
All right. Thanks. You have a good one, bud.
You too. Take it easy.
You too. Bye-bye. And that appears to be it. Bye-bye, everybody.